Hello, math humans. We're going to do 4.1 today. We're going to be starting our chapter on growth. So today, we're going to focus on linear growth. Later in the chapter, we're going to talk about exponential growth and decay, and then we'll end the chapter with logistic growth. Alrighty, as we get started, let's talk about linear growth. So linear growth means linear, so it means it's just like a line, and it grows by a constant amount. This constant amount is going to be our slope for each unit of time. And another thing that I would add is an initial population and initial number of bacteria. Whatever we're talking about for initial is always going to be when time is equal to 0 or when x is equal to 0. So that's also going to be the y-intercept. Okay? So those are the things that we're going to talk about with linear growth. Here is our equation for slope. Remember that slope is often represented by m. In this particular chapter, we're going to call it something different, so we'll get to that in just a moment. But it's going to be delta y over delta x, which is y2 minus y1 over x2 minus x1. So I've pre-written out our first example, and we're going to use that to help us manage our information. So in Flagstaff, the number of residents increased by 1,000 people per year. Key phrase, if the initial population is 4,680 in 1990, predict the population in 2025. Anytime you see the word predict, that means that you're going to have to write a model, or that means you're going to be writing an equation, and then you're going to use the equation to predict what happens at a later date and time. So from the information that's given, I'm going to write down that my initial population is going to be the 4608, oops, that's an 8, 0. And so this is going to also be the y-intercept, and that's going to be what happens when time is equal to 0. Okay? So in previous maths, because this is linear, we would have said that f of x is equal to mx plus b. Well, in this particular situation, the b, and it's always the y-intercept, but that's when time is equal to 0, and this is going to be how much our population is changing by. So this is how much our population is changing. Remember, a triangle means change, changing by. So I can write a linear equation for this situation, and so I'm going to write f of x is equal to, it's changing by 1,000 people per year, so this technically is our slope, or how much my population is changing each year. So it's going to be 1,000 times x, and then plus, this is the y-intercept, or that initial population, so 46080. So there is my model, okay? And then I'm going to predict what happens in the year 2025. So we need to do a little bit of math. So if I do 2025 and I subtract 1990, I'm going to get that that is 35 years. Okay? So I want to predict f of 35. So that's going to be equal to the 1,000 times 35 plus the 4680. And we're going to get that the population in 2020 is going to be 81,080 people. And remember, we always want to include the units, okay? Alrighty, and just so we can check what happened, the actual population in 2019, this is just information, was 72,402, and this came from some news source. But this is what we're doing. This is just fun information. So in this particular chapter, we're going to talk about linear growth. So previously we would have said f of x is equal to mx plus b. But oftentimes in this particular chapter, we're going to be talking about population. So they rewrite the model a little bit. So they say it's going to be p sub 0, and I'll define the variables in a minute, plus t times d. So these two formulas are exactly the same. They just have different variables, okay? So p sub 0 is going to equal the initial population. And if you think about a graph, right, that's going to be, there's the initial population. It's going to be the y-intercept. And that happens when time is equal to 0 because our y-axis is going to be population and our x-axis is going to be time. Okay? Alrighty, so t is going to represent time. D is technically the slope. The book calls it the common difference, meaning that all of the values change by the same amount, same difference, okay? And so we're going to use this situation when we do our examples. And so this is going to be the equation technically that the book wants you to use. Remember that it's the exact same formula that you've been using for a long time. The only thing that has changed is what we call the variables. So now let's do example number 2. Okay, so in this one, except you can't see it, Dora has inherited a collection of 30 antique frogs. The interesting thing to me is who would be collecting antique frogs. So each year she vows to buy 2 frogs a month to grow the collection. This is an additional 24 frogs a year. So how many frogs will she have in 6 years, and how long to reach 50 frogs? So we have 2 tasks that we need to complete. So I'm going to write down what I know. So our initial population of frogs, which I think is kind of gross, is my antique froggies. Okay, but we all like to collect different things. My common difference, D, so I'm going to write that this is the common difference, is going to equal 24, because it says right here that it's growing by 24 frogs a year. So my equation, P of t, is going to equal P sub 0 plus D times time. And so this is going to equal 30 plus 24 times time. Okay? So the first question was, how many frogs will she have in 6 years? So this, by the way, is our model. So now I want to use my model to predict, so how many frogs in 6 years? And so it's going to be the 30 plus the 24 times 6, and we're going to push buttons on our calculator, and we're going to get that this is 174 frogs. So I would identify my answer as well, and I'm going to write this is 174 frogs. So we've answered question number 1. Question number 2 says how long to reach 50 frogs. So now we have to do a little bit of algebra. Okay? So did I write that down right? I did not write that down right. My bad. This is, so I'm looking at my work thinking something's not making sense. My bad. 510 frogs. So how long till she gets 510 frogs? And that's a lot of frogs. And what are you going to do with all those frogs? So if we set up our situation, so we're going to say 510 is equal to the model that we had, 30 plus 24t. I'm going to subtract 30 from both sides. So I'm going to get 24t. 510 minus 30 is 480. I'm going to divide both sides by 24, and I'm going to get that t is equal to 20 years. So it's going to take her 20 years to collect 510 frogs. That's a little bit entertaining. Alrighty. So for example number 3, and this is our last example for today, we're going to talk about depreciation. And you will hear this word a lot as an adult. So a car depreciates, meaning that it's going to decrease in value by the same amount each year. Same amount each year means that it's going to be a linear change. Joe purchased a car in 2010 for 16,800. In 2014, the car is worth 12,000. And so then I want to find the model. So our first task is we're going to find the model. And notice it says linear decay. It's decay because it's decreasing. Okay? And so just to make sure that we understand that if something is increasing, it's going to be called growth. And if something is decreasing, it's going to be called decay. So find the linear decay model, and then how much is the car going to be worth in 2020? Alrighty, so those are our two tasks. So I'm going to start by writing what I know. My initial price of the car was 16,800. My car is, they don't actually tell us the slope, so we're going to have to figure that out. So for my slope, I'm going to do new minus old, and then I'm going to divide by time, which is the same thing as doing y2 minus y1 over x2 minus x1. Okay? So my new price is 12,000. The initial price was 16,800, and then technically it's 4 minus 0 because he bought the car in year 0. And so if I do that math, I'm going to get that this is negative 1,200, and then the time is going to be per year because these are years in the denominator. So this is going to be our D. Okay, so this is our common difference. So now if I write the model, remember that the generic equation is P of T is equal to the initial plus the common difference times time. So if I write my model, so P of T is going to equal my 1680, so that's how much I paid for the car. And then I'm losing, so this is going to be minus 1,200 times time. Okay, so this is my model. So this was our first task. Our second task is how much is the car going to be worth in 2020? So if we bought the car in 2010, to get to 2020, so 2020 minus 2010 is going to be 10 years. So I want to do, let me scoot my paper up, I want to do P of 10. So if I substitute those numbers into my equation, it's going to be 16,800 minus 1,200 times 10 years. And if I do that math, in 10 years, that's a zero, sorry, my car is going to be worth $4,800. So P of 10 is equal to $4,800. And if you remember the discussion that we've had about financing a car, simple interest, you're still going to owe money on the original price of the car, and in 10 years it's going to be about a third of what you paid for it. So that's just kind of interesting. Alrighty, that is it for today. I will see you soon.